He said, no, you need to publish that. So he talked me into writing a 2-pager for Communications, the ACM, reevaluating Amdahl's law. Everybody is messing with that standard. So we're back in the zoo that we had before there was an IEEE standard. And they're so much more accurate that you don't have to use 64 bits everywhere. These days, memory bandwidth is everybody's problem. It used to be just HPC's problem.
From Orion X in association with Inside HPC, this is the At HPC podcast. Join Shaheen Khan and Doug Black as they discuss supercomputing technologies and the applications, markets, and policies that shape them. Thank you for being with us.
Hey, Sheen, great to be with you again.
Hey, Doug, how are you?
Good. We have a very distinguished guest with us today. Really happy to say that we have Professor John Gustafson, one of the premier computer scientists of his generation. He is former chief product architect and senior fellow at AMD and former director at Intel Labs. Currently, he's affiliated with Arizona State University as a visiting scholar. John, thanks so much for joining us.
Great to be on. Thanks, Shaheen and Doug.
Hey, John, thanks. What a great pleasure. I met John first many, many years ago.
We're old. Yes.
And I learned a lot from him. He was the first person I heard who was highlighting the importance of memory and memory bandwidth decades before everybody else started talking about it. The other thing I remember that I want to actually start with, John is a graduate of Caltech, where Richard Feynman was a professor, and he actually was a student in one of his classes, including that famous bongo picture. So, John, maybe you start us there. How did that all happen?
Yeah, Feynman, we just adored Feynman, of course. We had lots of Nobel laureates on campus. There were about 38 Nobel laureates associated with Caltech. So the ratio of undergrads to Nobel laureates is about the same as the ratio of undergrads to faculty members at most places. Of all those Nobel laureates, I don't think anyone commanded the respect that Feynman did and the adoration, because he was funny, he was incredibly smart, incredibly good at solving problems, but just a very approachable guy. And besides being in his class, I actually thought he would be great for a cameo in the Caltech musical. We put on musicals not unlike high schools sometimes do, and we did a Guys and Dolls. And I thought, well, he's great at the Brooklyn accent. He can be the guy at the other end of the phone booth. But we also needed a bongo player for the scene in Havana, Cuba, which opens up right after the entr'acte. And you should have seen the reaction when the lights came on and we hit him with a spotlight. He's wearing a sequined top that's tied in a knot at the chest.
Oh my gosh.
And I've got pictures of that. And he had a great time. At first, he thought it was going to take too much of his time to be in the show, but then we couldn't get him off the stage. He said anybody who's actually seen recordings of him lecture knows he's just a master showman. He loves getting up in front of an audience. He can't resist. And that's what I was counting on. So he said yes. And I think he's done other cameos in the student musicals since then. And it always gets a huge reaction out of the audience. Like, that's fine. They all whisper and the heads all turn toward each other.
Nice.
That's brilliant. Now, of course, his name keeps coming up these days a lot more than it used to. In context of quantum computing, because he pointed in that direction first.
Yes.
What's your perspective on quantum computing these days?
It's a brilliant combination of the speed of analog computing, but with digital qualities to it, since it is discrete states. And I don't think people appreciate that it's a completely different approach to computing. It's not like you're going to plug a quantum accelerator into your server someday. It's just going to be a different way of doing things. I think we're still at the stage where people spend 10 months trying to figure out how to program, then it runs close to instantly. So the program ease is going to be a big hurdle, but it's certainly an exciting thing to consider and to look at. And if Feynman saw that it was eventually going to be the right way to go, I tend to think that he's probably right. He wasn't wrong about very many things.
That's so true.
So, that cliche that there are some technologies that are always 10 years away, you're not in that camp with quantum.
No, and I would never say so, even if I thought it, because I never get in the way of people who are actually doing things by saying, oh, that'll never work. I remember so many fuddy-duddies saying that to me when I was 30 years old about parallel processing, for example. And I thought, I never want to be one of these guys who says, this is impossible, it'll never work. The elderly and distinguished scientist who says something is impossible is probably wrong, as Arthur C. Clarke puts it.
Yeah.
Well, I love your sentiment. I mean, to my mind, over the last 4 or 5 years, I think we've reached a critical mass where there's so many super smart people and so much money directed at the problem all over the world. A, that indicates it is a solvable problem. And B, if you have that many people involved who are so intelligent, there's going to be breakthroughs. And it seems that we're just making these incremental breakthroughs across a broad quantum computing front. We hit this piece and that piece and this piece and take 2 steps forward kind of thing.
Get things up to room temperature and stable, and we're off and running.
Now, that's a good segue into parallel processing, since you brought it up. And kind of fast forward to, I think it was only a few years after I first met you, when you were leading the Floating Point Systems T-Series, one of the first massively parallel processing systems. You want to start us with that? And because that led to the Gordon Bell Award, which I also want to talk about.
Sure. It's funny how much of the hypercube technology of that era came from Caltech. I overlapped with 4 people who built the first hypercubes at various companies like Amatec, N-Cube, the JPL. They were all building hypercubes, and they were all there at Caltech when I was there, including Chuck Seitz, of course, who really did the first one called the Cosmic Cube. But at FPS, we said that's the way to go. Distributed memory and distributed processing, each one being its own autonomous computer. All this shared memory stuff is causing race conditions, and that's why people laugh at parallel processing is always the technology of the future. It will always be the way the technology of the future, because it never works right now. But if you get absolutely repeatable results, with the message passing paradigm, then you can really scale these things to dozens or even thousands of processors. And we immediately started working on this. And that's when I immediately started finding that all the customers said, it'll never work. Have you ever heard of Amdahl's law? And I said, well, things scale. And I tried to present it to them that way, that it's a mistake to use the same size problem and then go to 1,000 processors. That just makes no sense whatsoever. So eventually I found a way of putting it at Sandia when we were actually working on a 1024 processor N-Cube. And I showed it to Ted Barsis, and he said, you've got to publish that. I said, what? It's just common sense. It's just as the way speeds add, harmonically or as an average, depending on whether you fix time or you fix distance. He said, no, you need to publish that. So he talked me into writing a 2-pager for Communications, the ACM, reevaluating Amdahl's law. And I just couldn't believe the impact that had, because as I said, I thought it was just common sense. But we needed that argument because we were about to submit to the Gordon Bell Award people that we had gotten 3 massively parallel applications, real world applications at Sandia, to run at incredibly high efficiencies, like over 1,000 times faster. Even if you didn't scale them, they ran like 600 times faster. So it was still pretty good, even with Amdahl's law. But that laid the groundwork for, I think, the watershed where people went from thinking parallel processing would never work to its mainstream computing. IBM had announced the products like the SP2. Digital equipment got behind MassPAR, and all kinds of things started happening that it was a serious wave of the future that people took seriously. But before that, it was like quantum computing is now, just struggling to get anything to work.
I think, like you were saying before we started recording, was that it not only demonstrated that it would happen, it also explained why.
Yeah, the way you get people to change their way of thinking is you have to show them real experimental results on realistic applications, and you have to have a theory behind it that backs up, and here's why this works. And you get those 2 in combination, and it's powerful. People cannot then refute what you've done.
Yeah, totally. Now, that one was with N-Cube, right? It wasn't with IPSC.
That was with an N-Cube, yes. Mm-hmm. It could have been with an IPSC, but you remember the IPSC only went up to 128 processors.
That's right. At that time, you're right. It had to go all the way to ASCII Red or something before it...
Yeah. The N-Cube went to 1024, and it was very similar to a Blue Gene.
Right.
It's like the Blue Gene was based on it, but it wasn't. I think they independently arrived at the same idea of a little tiny daughter board that only uses 17 watts and is fully just memory and a processor. That's it.
Yeah.
Very elegant. So you can cram 1024 of those into one cabinet and get really a single clock to control the whole thing. It was a beautiful machine to program. Really, really good to program.
Yes. Well, I remember back then it was one of the first, really only, this level of a scientific computing achievement that was covered in like New York Times.
Yeah.
It was a popular journal. It was like for the masses now. And that was a watershed.
I heard a radio show. Paul Harvey actually announced it on his radio show.
Oh, darn.
He got 1,000-fold speed up. I thought, whoa. And it was read into the congressional record, actually.
Wow. So you were part of the rest of the story.
Yeah.
That's good. Now, John, I understand you're one of the few SC perennials.
Yes, 1988. Actually, We'd just done the work to show that parallel processing worked. That was like October, I think. And we'd submitted it. And then November, the very next month, was the first supercomputing conference in Orlando. So the bomb hadn't hit yet. And Seymour Cray gave the keynote, and he was talking about possibly going to 16 processors, but he thought that might be the limit that he'd ever go to. And my colleagues at Sandia, Gary Montre and Robert Benner, we just kind of smiled at each other. You have no idea what's about to hit you, Seymour.
Nice.
Yeah, but I got to tell you, John, discovering Amdahl's law was really disappointing because I was at Clementi's lab at the time, and we were doing parallel processing, and we had 3 and then 10 attached processors, FPS attached processors, hang off of a mainframe. And we were running applications and measuring them, and we were plotting them. And, I didn't know anything about Amdahl's law. I was like a chemie. So I was just plotting these, and I just sort of dawned on me at some point that, you know what? We could never do better than 4x.
Yes. Well, I remember Clementi saying that my Gustafson's law was a bunch of nonsense, that he wanted to just run a particular size problem. And I said, Enrico, I remember when you did a simulation of 81 water molecules using, I think, is it 3-body approximations? And no one had ever done a problem that big. When we increased your processing power by a factor of 10, suddenly you wanted to do 243 water molecules.
Yeah.
So you're a perfect example, actually, of scale speed up. If I give you more power, you will run a bigger problem. Any chemist will. Any scientist will. That's
Exactly.
we live. We all live at the same rate. I have yet to see a technology that reduces an 8-hour workday down to 1 hour, so we all go home and just don't try to do something more with all our hours of time.
The genius of it was that you plot those curves and you realize that, okay, your app is 95% parallelizable. And for it to really show those kinds of speed up, it needs to be 99.99% parallelizable. Is that ever going to happen? And I think the genius of it was that when you grow the problem, the part that is parallelizable grows faster.
Almost always.
And that was, wow, okay, that unlocked it.
Yes. Or some people see it as, if I've got part of this running in parallel, part of it in serial, how much longer would it have taken if I had to do the whole thing in serial? So that turns it upside down. And then the formula that you get if you calculate what that speed up formula is does not have an asymptote. The length of time it would have taken you to do a serial program, even if it's only 1% parallel, but you used, let's say, 1,000 processors on that 1%. Now, how long would it have taken you to do that in serial? A lot longer. And you use that as the speed up. If you really want to use that kind of a ratio where the workload is exactly fixed.
I think that's what justifies using GPUs, even when they're not anywhere close to fully utilized, right?
Sure, absolutely. I point out to people, driving around in an SUV, do you feel bad that your other seats are not occupied? It's just you driving. You can seat 8 people in your SUV. Isn't that incredibly inefficient? Or let's say you buy a piano and you're only playing like just a few notes at a time, but there's 88 of them. So what you need to do is lay a board across all the keys and push it down over and over again as hard as possible. Then you'll get full efficiency of the piano.
Full utilization. Exactly.
Yes.
Perfect. We mentioned SC perennials.
Yes.
And for folks who don't know, that means I think there are a dozen of you who have been to every single
I think it's 17. Sometimes only 12 of them will get into the picture because they're not all present when they gather people for the photo. But I'm pretty sure there's still 17 of us. And
17.
I'm the second youngest one. There's one person who was a grad student when he attended the one in Orlando. I had already got my PhD and got my first job. So, if this goes on long enough, I may be one of the very last ones standing. So I wouldn't miss it for the world.
Awesome. So we'll be seeing you in Dallas in November then. Very good.
Looking forward to that. And also thank you for what is now known as the Gustafson law. So not everybody gets to have a law named after them. So congrats there. That's really
opened a lot of doors for me and amazed me.
Absolutely.
Everybody thinks they meet me and they say, "Why aren't you dead?" People's laws named after them have to be dead, don't they?
That's quite a compliment, I guess, maybe.
Well, not everybody would know that John and I also got to meet the actual Gene Amdahl. When he was living, because he was an advisor to one of the companies that John was affiliated with and ran for a while. Yeah,
I've gotten to have lunch with him a few times, and he was always, I think, regretful that his law was abused the way it was.
Yes.
As an excuse against parallel programming. He really meant it to apply to SIMD machines running an operating system, where the operating system instructions are like 15 to 25% of the instructions, And you can't get rid of the operating system. Therefore, you are limited on that kind of a design, when he was debating with Slotnick about the ILIAC 4.
That's right. That's right. He did tell the story of debating Slotnick, and they don't make him like those guys anymore. Yeah.
Yeah, well, people did not want to have to convert all their code from serial to parallel because it is painful and it's expensive to rewrite code. So for them, Amdahl's law was a fortress that they could hide inside. Say, it doesn't work. I don't have to recode anything.
Oh, interesting.
Yeah, that's the people have the real strong affection for Amdahl's law and will not let go of it. And I can think of some professors at Stanford. I think that's really what's underlying it all.
Interesting. Now, sometime after this, having kind of solved the problem of how do you look at scalability, you got interested in IEEE arithmetic.
Oh, yeah.
And what I consider the challenge of mapping an analog space to a digital space.
Well, the overlap is, when you go parallel, we discovered this on the N-cube, we were getting slightly different answers. Of course, as soon as you get a slightly different answer, you said, oh, we probably had a bug, especially with something as complicated as programming 1024 processors. And we discovered it wasn't a bug, it was the lack of associativity in floating point arithmetic. And even in the early 80s, I was trying to find some way of doing computer arithmetic that would be less prone to rounding error or closer to true mathematics. And it's a very, very difficult problem. And I think 33 years later, I have something I can point to and say, this is a pretty darn good solution. But it is a tough thing to do. And, IEEE arithmetic did make one big step forward. It got everybody to use the same position for the sign bit, the exponent bits, and the fraction bits. And so now you could actually trade data between machines. But almost immediately things started breaking down and they started taking little variations. Now what's happening now is that the IEEE standard in hardware is almost extinct and people don't realize it. If you actually look at that 100-page document and all the things you're supposed to do, a lot of them are simply trapped into software now. And so if you have an exception, a subnormal or a denormal number or an overflow or not a number, so any of those things, they trap it to software and it can take 200 clock cycles, even in microcode, to deal with it. So the hardware assumes only a normal floating point number and hopes that you never stray off out in these exception regions. And they're not supporting it on GPUs. GPUs also assume a normal floating point number. It's being stripped down, especially for the AI applications. As they go down and down in precision, you start to notice the warts of IEEE's 754 standard become more and more obvious. So I started just a very different tack of saying, let's assume if we had 2 bits, what would be the best possible use of them? What about 3 bits? What about 4? And how do you design that? And I discovered the mapping to the projective reals. And a very elegant solution exists to map signed integers to signed real numbers. It's not just cobbled together the way people tend to think of, well, let's make this field mean this, and this field can mean this. And here's a special case we can make for this field, the kind of design by committee that led to IEEE 754.
Right. So you've been at this for a good number of years now, and it has grown up, it has matured.
Yes, it's ironic. My first job was at a place called Floating Point Systems because that's all I do now.
That's so true.
Yeah, this is my hot button right now. I remember when I proposed a new number system to Justin Ratner, this is the CTO of Intel. He said, well, you can't boil the ocean. And I immediately thought, you mean I can't do it again? I've had some practice at this. And guess what? The ocean is boiling when it comes to number formats. First of all, you've got B floats from Google. You've got DL floats from IBM. And then everybody's playing games with 8-bit floats, like Tesla has got 8-bit floats that have 4 bits of exponent or 5 bits of exponent. Everybody is messing with that standard. And I think NVIDIA has several formats of their own that have nothing to do with IEEE. So we're back in the zoo that we had before there was an IEEE standard. And I'm glad to see it because if you can't get people to open their minds to changing the arithmetic at all, that makes it hard. But now they've already agreed we need something better for AI. And that opens the door to things that are better for high performance computing as well.
Right. So lay the scene for us, if you would, with what started out as, I remember you writing the book, more than 10 years ago.
It was, I think it started 2013 is when I started writing it and finally got it to press in 2015, the end of error.
Right. Okay. Right. So, it feels like about 10 years ago. So it's in the ballpark.
Yes.
And it was called Unum at the time.
Yeah, Unum arithmetic.
And then it kind of morphed over time. So kind of take us through the trajectory of that, if you would.
So I was trying to be friendly to IEEE and say, here's an upward extension. I'll call them universal numbers that allow you to admit when your answer is not exact. That it's between two representable numbers, like an open interval between two numbers you can express exactly. It's sort of like when you write pi equals 3.14, that's a lie. But if you say pi equals 3.14 ... now you're telling the truth. It's a very quick way to say it's between 3.14 and 3.15. There's some other bits past that or digits past that, and now you've made a true mathematical statement. Well, that the difference between a ... or not having a ... is just one bit. It's like a sign bit in the beginning and a uncertainty bit on the end. And then I made that variable precision, which is what William Kahn said we always really needed in interval arithmetic, is variable precision interval arithmetic. And I rebuilt numerical analysis from the ground up in that book. And everybody liked the book. It was in its category in Amazon. It was #1 bestseller for a while against 4,000 other books on that kind of subject. But they all said, people told me, this is not hardware friendly. I did it in Mathematica as a model. I kept it as close to hardware as I could, but I recognized that having variable size makes something nasty for hardware. You want to be able to index into an array like a matrix.
I thought Rex was trying to do that. Did they not implement that when they were building a chip?
Rex Computing did get my latest kind of form of arithmetic done, and somebody has built a Unum chip, actually. I think there's a couple of them. One of them is in Asia, and I'm just amazed that they did it. But I think it's fairly fast. I haven't timed it, but in any case, my quest, Singapore got very interested in the idea of a new kind of arithmetic and asked if I would continue my research under their auspices. And wow, what a privilege. I mean, to go to Singapore and be paid to do what I was doing for fun, because I just got to know the answer. And what a fabulous country Singapore is, I have to say. One of the best run countries on the planet. My whole mission was make it hardware friendly. At least make it at least as good as floats if I possibly can. And I made some progress, but the breakthrough was on December 3rd of 2016, which is just after I had a big debate with William Kahn defending.
I remember that. Yeah.
He was attacking the idea that we could end error, and he really didn't like the title of my book. He didn't read very much of it, but he knew he didn't like the title. But at December 3rd, I finally got the mapping of the projective reals to the two's complement integers. That it just feels right. Once you see it, you say, yeah, that's elegant. It reduces the IEEE standard down to about 12 pages of explanation for how do you do it. And by this time, I'd gone through a type 2 Unum and a type 3 Unum, and I decided to call these, I wanted to call it a guess. And I thought that's too pejorative. Let's be more optimistic and call it a posit, which is an assumption that something that you think will prove to be true. You posit something. I also like the fact that it was 5 letters, so people could change all the words float to posit and wouldn't change their pagination. I presented at Stanford on Groundhog Day in 2017, and there's a course called EE 380 that they invite people to come and give guest lectures, and they let their students view these on YouTube. You usually get about 300 views. It's like Dave Ditzel went on and explained his approach to computing, and people get to hear what new product has been announced sometimes from, say, an AI company. So I did this lecture and I introduced positive arithmetic. It's about 60 minutes long. You can still find it there. And to my astonishment, it went, by the standards of this kind of subject, it went viral. 26,000 views.
Oh, yeah, that's viral. That's right.
And how many? 26,000?
26,000. I wish I could put it in my citation index. I can't put video watches a citation. I'd be off to the races. But that was the beginning, I think. And it was very unlike parallel processing, which even to this day, it's like pulling teeth to get people to program in parallel. They don't teach it in the schools. They might introduce it when you're a junior or senior as an undergrad in computer science, but they still start by teaching you serial programming. And then it gets kind of in your head, and it's harder to think about things running in parallel. But when I said I had a better alternative, floating point arithmetic, people screamed, hooray! God, I hate that stuff. Finally, we've got something that's clean and even has the possibility of associative arithmetic at last. And you'll get the same answers in parallel, and it will be repeatable, and you won't have differences between math libraries where people round slightly differently and it makes the answer diverge. All those problems can be handled if you follow the rules of positive arithmetic. Instead of pushing like Sisyphus, the rock up the hill, suddenly it was more like watching a forest fire. And Soon I had like 200 groups working all over the world on implementing posit arithmetic, mainly for RISC-V, which was very satisfying because what really triggered the breakthrough was Kurt Cavill of the RISC-V committee saying, we want a better kind of way to represent real numbers for RISC-V. Can you design something for us? And that's when I really started sweating bullets, because I know what it means to make something hardware friendly, depend only on integer operations that you can actually build. And it has come full circle. We're sticking posit arithmetic into RISC-V. There must be about 30 projects to do something like that. And real native VLSI is coming out in about 3 months from a company called Caligo Technologies in Bangalore. So they're really doing tape outs and going to see. They did something very clever. They did a multi-core where some of the processors use float and some of them use posit. So it's a perfect thing for apples to apples comparison. You can experiment with one or the other without changing chips.
Oh, interesting.
Yeah, great idea. By the way, cool. the European Processor Initiative,
yes,
yep,
they're using posits.
Oh, is that right? I didn't know that.
Well, they have two parts to their project. There's the main CPU. I think that's based on ARM. I'm not sure about that.
I believe so, actually.
And then they have the coprocessor. And the coprocessor, the accelerator, is the lead company on that is Calray, and the CTO is Benoit de Denichan, and he is all over posits. He has said he's committed that that's what they're going to use for their numerical accelerator. So
very cool.
These things are real, and they're coming.
So the ocean is warming up. Maybe.
Yeah, it still takes 10 years. Even when you have an idea that's as good as, let's say, the fast Fourier transform. After that was discovered and rediscovered in 1962, it still took about 10 years before people were using them. And It seems like this is just the way. There's too much inertia in the way we're doing things now. But there's enough tools out there, both software and hardware. Some of these companies have a complete stack, hardware and software, that is all posits. The benefit is they're more accurate in general, and they're so much more accurate that you don't have to use 64 bits everywhere. You can use 32 bits and just do the accumulations perfectly using part of the standard says you can always accumulate perfectly using a register called the quire. There's exact dot products and exact sums up to like billions of elements.
Oh, wow.
So, John, is it fair to say that on the inertia issue, that bringing something new to people who already know everything, there's kind of a conflict there. There's an inherent conflict.
Like Isaac Asimov said, those of you who think you know everything are bothering those of us who do.
Actually do, right. One thing I like to ask book authors, and there's a quote from George Orwell who said, writing one of his novels, he said it was like suffering through an affliction that had to run its course. But it was just hell.
That's not what I would put it. I was told that writing a book is a lot like having a child. And I think that's a better analogy. It feels like a baby.
That's a good analogy. Yeah.
You don't know how to do it. It's the first time, and you hope you get it right.
There's a lot of pain and agony at the end, I guess, or throughout. And then, voila, there you have it.
So, I will have a second book out. I think working title is Every Bit Counts.
Right.
Nice.
Well, actually, that reminds me. One of the things that, John, I know you presented one time in one of the talks I attended was about minimizing energy for different activities. So what's your perspective on that?
That's the underlying theme of everything I do, is I'm trying. These days, memory bandwidth is everybody's problem. It used to be just HPC's problem, but now it's everybody's problem. And that's where most of the energy goes. It's also where most of the dollars go, is in the communication parts of the hardware. That's where your energy and your power and your dollars are going. Then that's the thing to speed up. And we've done everything we can with caches and tricks to make memory look better, but no one seemed to have looked at, have you tried making the operands smaller, but still adequate for what you want to do? And I said, you're throwing 64 bits at everything. And you probably only need it for a very few places. That was the original intention of double precision. But because people feel that they don't understand enough about numerical analysis, and I don't blame them. I don't think everybody should have to know numerical analysis to use a computer. But they just say, here's my panacea. I'll just ask for 64-bit floats and then complain about how slow my problem runs.
Right.
But you get more than twice the speed if you go to half the precision. I'm discovering I can solve huge linear systems much better than 64-bit floats than using only 32-bit posits. because I can check the answer. I can actually do the dot products and find a residual, and the residual is exact. I can use that to correct any errors. You can't do that with floats because they don't have the concept of an exact dot product. In fact,
That's right.
the IEEE committees rejected it repeatedly, say it's way too expensive. And for floats, it is. The register has to be like 6,000 bits wide.
Mm-hmm.
But I can do with 256 bits.
So what does this do to things like interval arithmetic? Is that already incorporated now, or would you still need it?
The interval version of posits is called a valid, another 5-letter word. And valid is a pair of posits that have the uncertainty bit
I see.
at the end of it. And so all the things that are in my book, The End of Error, will apply. And I will devote a couple chapters showing what they can do. But once again, you get the full power of being able to express any set in the real number line. It's not just intervals, it's sets. So if the set of points is, let's say, I don't know, negative infinity to negative 1 and 1 to infinity.
Mm-hmm.
I think that's an arcsecant or something like that.
Right.
Right. Then I can express that just as easily as I could say every even number or something like that. So once you can express sets, that's what real number arithmetic should be about. You should be able to take complements and intersections and unions and say the result is somewhere in here. And if somebody says that's not exact enough, I say, well, you can use more bits. But the framework is there to get it as exact as you want it to be, and you'll have full confidence in the answer. But the funny thing is, as long as I've been working on interval arithmetic, I've discovered that maybe 1% of the customers care about getting an absolutely provable right answer. And the other 99% say, just give me something that's good enough and as fast as possible.
I see.
So I followed the market.
Nice.
So I put a lot more emphasis on the posit ones, which guess their way through a computation and do a pretty good job and are much better than floats in every respect. But the book will certainly cover how about if you use them as endpoints for intervals and have the uncertainty bit, the ... at the end. You can do all these very powerful things.
Now, let me ask, we started with 32 bits, 36 bits, went to 64-bit. Now we're moving our way back down to 8, maybe even lower with AI.
Yeah.
Do you see a need to go back up again and say that I really need 128 bits? Or are we kind of done now?
David Bailey has spent a lot of his career searching for applications that require very high precision, and he's written books about that. He's found a few. They're rather rare because people tend to express the inputs. They only need maybe 4 or 5 decimals in the inputs, and they only really need no more than 5 decimals in the output. So I think if there's something that tells you really need 128 bits, it means you don't know what you're doing. John von Neumann once said about double precision, he says, if it's not worth doing, it's not worth doing well. I really think that the direction we should go is reduce the precision. Some people call it approximate computing, and I laugh because what do you think floating point is?
Right.
You think that's exact? You're already doing approximate computing. You're just making it a little bit worse. But I'd say get the highest quality you possibly can out of whatever bits you're dealt. Make sure that there's a maximum information in each bit. In a way, apply information theory, Shannon's information theory. Make sure that every bit pattern you design is used about the same number of times, and then you'll have maximum entropy. But that's not what we have now. I mean, we've got some of the bits never change in a floating point number because you don't need 10 to the 300th power very often.
You're saying some bits are more significant?
Well, it's just crazy that we have these big dynamic ranges.
No, I get it. Yeah. You're absolutely right. Yeah.
They don't fit the applications. Every application I've seen has a tent shape or bell curve shaped distribution of numbers that it actually uses. And it's always going to be that way because people were always afraid of underflow and overflow. So they try to avoid those. So they're already centering their computation somewhere with numbers that are human understandable, like magnitude 0, that is 1. All the existing applications are ready for just a drop-in replacement with posits, which have a tapered accuracy. The very small and the very large numbers do not have as many bits of precision. They automatically taper the precision down, but that gives you more bits of accuracy for all the numbers you use, like between 1 millionth and 1 million. Those numbers are going to have maybe 4, maybe even 10 more bits of accuracy. There's 60 bits of accuracy in the double precision posit of actual significance. That's a lot. But if you've got this quire register I mentioned, that's got like 60 decimals of accuracy, something like that.
Yeah, that's plenty.
Yeah.
So, John, looking forward, based on everything you're seeing, hearing, doing, and then if we want to look out 5, maybe 10 years, do you see a significantly changed supercomputing HPC landscape, or incremental progress, but not looking a great deal different?
Oh, I believe there could be a breakthrough in quantum computing. As I say, if somebody discovers a different way of storing a qubit that's much more practical and sticks around for minutes, not milliseconds, then that's going to be a huge, huge watershed. But the incremental improvement I see is people are finally starting to think much harder about how do I make every bit count in the computer? Because Moore's law is not doing what it used to do. And if I can have the precision, well, that's like one turn of Moore's law. I used to have to wait 2 years for that. But if I can do it in software, or I can do it just by thinking about the bits differently, then I can keep Moore's law going at least one more generation, maybe two.
And that's huge. That's huge.
That is kind of huge these days.
Yeah.
We're happy to get 10% more on things. The real news, I think, these days is the fusion of AI and HPC. They really are, they're naturals for each other. Multiply adds upon multiply adds. That's what both groups do. Just whether it's dot products for linear algebra or dot products for neural networks, it's the same architectures, and they're just being used with lower precisions, but the same kind of techniques apply, and that's eventually going to make people really think about right sizing all of their precisions to what they're trying to do, instead of being sloppy about it.
John, it's been such a pleasure for me. You have a great passion for this stuff and great enthusiasm. And that's wonderful.
I've had fun with you guys. Thanks for having me on.
Absolutely. Always a pleasure, John. Thanks for making the time, and looking forward to more later.
Sure.
Okay, thanks so much.
Take care.
That's it for this episode of the At HPC podcast. Every episode is featured on InsideHPC.com and posted on OrionX.net. Use the comment section or tweet us with any questions or to propose topics of discussion. If you like the show, rate and review it on Apple Podcasts or wherever you listen. The At HPC podcast is a production of OrionX in association with Inside HPC. Thank you for listening.